Presenting today, we have Michelle LaRue of the NOAA Climate Prediction Center. Michelle has been with NOAA CPC since around 2004. Her activities include leading the NOAA ENSO Outlooks team and contributing to the climate.gov ENSO blog as a writer and editor, where she's coordinated and edited over 150 articles. Her research is focused on intraseasonal to interannual climate variability with a background in atmospheric science. Recently, she's been awarded with the National Weather Service Isaac Klein Award at both the local and regional level for making significant contributions in support of the National Weather Service. And we are very excited to have her join the PPAI panel this year and are looking forward to her contributions, including this webinar. So with that, please go ahead, Michelle.
Can you hear me okay? All right, great. Thanks so much for that introduction. I really appreciate having the opportunity to present this work. I'm giving two talks today, very distinct. And part of that is because the organizers of this committee wanted me to touch on the S2S precipitation products that exist over the United States. And obviously, because I work at the NOAA Climate Prediction Center, or CPC, that's where I'm going to focus the overview. The second part of this presentation will go sources of skill for wintertime California precipitation. And this is a research project that I've been working on and off through the last year or so. And I really want to credit Mike Tippett and also Emily Becker for their contributions to this work. All right, so we're going to start with the overview. Go to the Climate Prediction Center landing page, you see this, and basically it's an assortment of different climate outlooks. And they really span the gambit. I mean, they have, we have short term from 6 to 10 day all the way out to 3-month outlooks. Those 3-month outlooks are issued out to a year. So we really are responsible for that intra-seasonal bridge between the daily weather forecast and longer term climate. And so this can actually be a little bit daunting. There's a lot here, but I'll go through each product one by one. And obviously I'm going to focus here on the S2S products. First S2S product is 6 to 10 day outlooks. And I know that the interest here is mainly on precipitation. That map is shown on the right-hand side. Temperature is shown on the left-hand side. We issue these simultaneously, so that's why you'll see both. And so 6 to 10 day outlook is a 5-day average. And keep in mind that climate outlooks do essentially rely upon these averages. They're different from daily weather forecasts because they're showing the average. And often it's this predictability only arises because we're looking at averages. 8 to 14-day outlooks. So this is also known as week 2. Obviously a 7-day average. And then 8 to 14-day US hazards. And hazards is important because that's actually where you can get information on the extremes. There's a number of hazards that CPC forecasts, including wind, temperature, and obviously here I'm showing a map of heavy precipitation. And heavy precipitation is defined as 3-day accumulated precipitation exceeding the 85th percentile and 1 inch. And this was determined mainly because if you use higher threshold like 95 percentile, you have far fewer samples and the reliability is not as good. So for that reason, the CPC has selected the 85th percentile for the cutoff for extremes. This is our newest outlook that we issue operationally. It's called the week 3-4 outlook. And this, unlike the others, is a 14-day average. So it's a 2-week average starting at day 15. And then we have monthly outlooks. And this is, you can see the label there, revised. That's because the monthly outlooks are actually issued twice a month. There's a mid-month monthly outlook, and then there's a really at the end of the month. So for example, this particular case, this is a June forecast that was issued on the last day of May. revised monthly outlook. And so what is being shown in all of these S2S outlooks? Well, what I'm showing is probabilities. All right, so this is a percent chance exceeding a certain percentile in the climatology. So we find the cutoffs, and in this particular example, and in most of our products, we use tercile limits, meaning that we find the cutoff for the bottom 33%, the middle 1/3, and then also the upper 1/3. And so we have a below, near, and above average categories. And so we're looking and giving the probability that it's exceeding those thresholds for those categories. The maps can be a little difficult to look at, mainly because the color on the maps is the favored category. You have to keep in mind that there is a percent chance for the other two categories as well. In this particular example, this is showing December, January, February 2015-16, which was notable because there was a strong El Nino at this time. And if you look at California, for example, we have some probabilities that are about 60% chance for above average. That means 40% was in the other two categories. There was a chance for a not wetter than average season. So most of our products are in this format. Week 3-4 outlooks are a little different because they are based on two categories that have an upper and lower 50%. And that was done because at the time we started that, we wanted to see whether that was more comfortable to our users using an upper and lower 50 percentile. We're still getting feedback on that. So if you have opinions, please share that with us. So hopefully, if you hear a forecaster, and this is a prominent one in Washington, D.C., point to our outlooks and say, look, it's going to be cold, and it's going to be warm, and it's going to be wet, it's going to be dry. I hope that you can, correct that person. These are not showing, these are not deterministic. These are showing probabilities, the chances that it will be below average, the chances that it will be wetter than average. So what tools do forecasters rely upon? Well, it really spans a lot of different techniques and models, and really a lot of the choices here are due to historical reasons, or they're due to just simply the model design itself, because a lot of these models are not run every day. They might not be run far enough. And so as a result, the selection of model we use will depend on what we're trying to forecast. So for 6 to 10 and 8 to 14 days, we update that forecast every single day. There's a forecaster that updates that. And they rely primarily on calibrated or bias corrected model guidance. And we're using primarily ensemble guidance. Because we're dealing with probabilities, it's really important for us to have an ensemble so we can understand what the spread is. And so for that, we use the ensemble GFS. We use an ensemble Canadian. We also use the Euro. The forecasters often will just start with the objective model consensus. There's some tools that essentially combine all this information for us and recent model. And sometimes they'll take into account some recent model behavior. If you want to get an idea for what they're using, because it does vary from forecaster to forecast, you can take a look at the discussion. And the discussion will give you an idea of what is being weighted on a particular day. Have the week 3-4 tools. The week 3-4 outlook is created each Friday, so just once a week. And here, this is where statistical models start making a little bit more inroads. We have a multivariate linear regression model that uses MJO, ENSO, and trends. And then we use, of course, computer models, which must be run out to week 4. And certainly not all models are run out to week 4. So for these forecasts, we rely upon CFS, JMA, ECMWF, and SubX. Monthly outlooks are created twice a month. We, in these forecasts, have historically used CFS, the North American Multi-Model Ensemble, or NME, and then we also use a lot of statistical-based tools and their consolidation, such as CCA, canonical correlation analysis, or constructed analog, We also use a tool we call optimal climate normals, which is basically the trends. So for extremes, one of the newest tools that the forecasters use is available at that link shown at the bottom. And I really recommend you check that out because it's actually a pretty nifty tool. And it's showing week 2, and it's showing it globally. I've taken a screenshot here of the North America, but certainly you can get any part of the globe with this particular tool. And so it's relying on a calibrated ensemble GFS, and it is essentially for support in our 8 to 14-day US hazards. Again, we are looking at those 3 days and also in excess of that 85th percentile. So we're issuing forecasts almost all the time. You know, the shorter range or shorter lead forecasts we do almost every day. For the middle ranges, week 3, 4, monthly, we do that once a week or maybe a couple times a month. But there's a lot of forecasts out there, and it's important, I think, to verify them because verification builds trust in the forecast. It also gives our users some baseline from which to compare their particular tools. And so there's a nice link down below. Unfortunately, we've had a few technical glitches with it recently, but hopefully if you check that out, those have been ironed out. If not, just be a little patient, and I'm sure in a couple of weeks it will get back online. But anyway, you can pull up skill scores, and I'm showing Heidecke skill scores here because historically they've been emphasized as CPC, but there's other skill scores such as Brighter and RPSS and so on. And you can look at it temporally, like a time series shown in the top panel there, or spatially at the bottom panel. You can pick what average period you want to look at, top panel showing 8 to 14 day skill, or you can pick monthly, which is what the bottom panel is showing. And you know, clearly we tend to, at least for these particular forecasts, have skill in certain parts of the country. It's better than other parts of the country. You know, there's certainly some room for improvement. So if you have a particular tool, a particular technique that you're trying to, that you think would be useful for CPC, I do recommend going to this page and checking it out and comparing to the skill that we document here. Finally, I'll kind of wrap up this first part by talking about the sub-X models. Sub-X models is a collection of models that are run once a week from these various agencies listed here. And there's a multi-model ensemble shown in the bottom right. And what this page is presenting is forecast skills, correlation for temperature. And you can get this for week 1, you can get it for week 2, you can get it for week 3 and 4 together. Kathy Pajan put together this page. It's really quite nice. Not only can you see the verification, but you can also see the real-time forecasts. And if that's not enough, I really recommend checking out the sub-X data, which you can download at the IRI data library, that link at the very bottom. And in the second part of the talk, that's essentially the link that I used. I downloaded all of the sub-X models and I processed them. And you can create your own science that way. Okay, so I'm going to shift now to the second part of this talk. And again, I want to credit my collaborators, Mike Tippett and also Emily Becker, who have been looking at this off and on. And so why we started looking at it was really kind of motivated by the 2015-16 El Nino. This was a very historically strong event, a top 3 event in our historical record, going back to 1950. And the forecast for California, we at CPC had a 60% chance of above average or above median precipitation. And instead what happened is we actually saw below median conditions. So it was drier than we expected. And a lot of people looked at that and said, you know, that's a problem. You know, there's a failure there. But despite that failure, you know, we wanted to ask the question, well, all right, so maybe seasonal forecasts are tricky, but what if we look at this in S2S timescales? Maybe those precipitation forecasts have more skill. And in addition to that, what are the sources of the skill? Does ENSO contribute to S2S forecast skill? And also, what are the sources of error? So I'm going to start with some research by my colleagues at Climate Prediction Center, Arun Kumar and Mingyu Chen, who have looked at strong El Niños from different angles. And this is one of their earlier papers on this, where they used 316 members from the NCEP CFS version 2 model. So this is our primary model in-house that does seasonal forecasts. And what's nice about this particular model is it has a long reforecast and it has a lot of members. So it's run 4 times a day in real time. And in the reforecast, it runs about 15 days a month. So you can basically get a collection of different members from strong El Nino events. So in the observations, we only have like 3. So that's just not a lot for if you're trying to develop some robustness. But when you look at the model world, you can get a bigger collection and better understand the signal to noise. And what do I mean by signal to noise? Well, in this particular diagram, I'm showing December, January, February, California precipitation. This is a probability distribution function. And so the black line is climatology. It's basically all the winter seasons collected in that historical record and how California Precip is organized. As you can see, it's fairly Gaussian. It's centered roughly about 0, maybe a slight tilt toward the drier side. But strong El Niños will shift that seasonal average. And so when they picked out the strongest event, they got that red curve. And what you see is that rightward shift toward wetter conditions. So certainly stronger El Niños do provide some signal in the sense that that median, the peak of that curve, does shift toward a wetter extreme. But there are still substantial chances of a dry or near average outcome. So if you look at the area under the curve, the red curve there, less than 0, it's quite substantial that even if a strong event, there's still a % chance that you will get a dry or even a near average winter. And part of that is because the signal noise ratio over California is usually less than 1. If you look at top left panel there, that's the signal. So essentially the ensemble mean footprint, and the ensemble mean is an estimate of the signal. And by signal, I'm talking about the predictable part of a model forecast. And then the middle panel that is showing spread. So this is the distribution or the variance about the ensemble mean in an ensemble forecast. And then the bottom panel is signal noise ratio. And over most of California, it's around 0.7, 0.8. So what it's basically indicating is the spread is quite wide. A lot of times when we put out these forecasts, it's the signal that gets emphasized by our users. They like to take our forecasts and make them deterministic. They look at that signal and they say, look, it's going to be wetter. But I think it's important to keep in mind that we do have substantial spread, especially in seasonal forecasts, and especially for a target variable like California precipitation, where the signal noise ratio is less than 1. You and Arun also did publish a second paper more targeted at the winter 2015-16 El Nino event. And they took the ensemble and they did this very creative thing where they looked at the best 4 members. And these best 4 members are the members that are most similar to the observations, and the observations in 2015-16. And then they also compared it to the worst 4 members, the ones that are least similar to the observations. And so the SSTs, that top left panel and the middle panel, the best and the worst are actually not very different from each other. In fact, if you take the difference, you're left with largely a blank map, particularly in the tropics. So the SST pattern associated with those best 4 members is pretty indistinguishable from those of the worst 4 members. And then at the bottom is showing the precipitation pattern that resulted from the best 4 and the worst 4 members. The best 4 members, by definition, match very well to the observed pattern, particularly over the West Coast. You can see that it matches the wetter conditions that we saw in the Pacific Northwest and the drier conditions south of that. The worst 4 give you the exact opposite pattern. So within the spread of this seasonal model forecast, you can have a forecast or members that look very, very similar to the observations and those that are totally opposite of the observations. So even though there was almost this identical SST forcing, you can get these 2 very different outcomes from California precipitation for 2015-16. So seasonal average ENSO has a lot of noise, and that's very evident that, you know, it's almost irreducible. There's a considerable bit of a spread in these seasonal outlooks. So then the question is, well, how about on S2S timescale? Does ENSO have an impact on the subseasonal timescales? And if not, are there other predictors that we can look at here? Is there other ways to, you know, get a little bit more signal? So some of my collaborators at Columbia, Mike Tippett and his colleague, Dr. Wong and Adam Sobel and others, did this really nice study that's published in GRL. They were looking specifically at the 15-16 event and also the La Nina that followed it. And, you know, what they found was that they were, you know, like us, unable to get a lot of skill from these seasonal forecasts. But what they noticed is that when they start looking at monthly targets, especially in the winter, like January or December, they were able to predict the monthly average precip with lead times up to 30 days, which is really impressive. So 30 days in advance, they were able to get the right sign of what happened in California, that the drier conditions occurred. That was in the forecast beginning 30 days earlier for the monthly average. So that intrigued them. And what they noticed is that, of course, the zonal wind is fairly well correlated with California precip. And this is somewhat intuitive, especially given all the recent work in years about atmospheric rivers, which is some combination of water vapor and winds. And so they developed a wind index, which is the difference between those 2 boxes in that top left panel. And that wind index, as you can imagine, for a daily average is kind of noisy. And so if you were to correlate that wind index with California precip on a day-to-day basis, you'll get correlations on, at least in the winter, about 0.4. But something starts happening when you start averaging things out. Remember, we like climate outlooks are averages. So the 714 to 45 day average is shown on the x-axis. And the correlation actually increases between the zonal wind and California precip. So there's a little bit of an emergence here of a predictor that may provide some signal. And so one of their arguments in this particular paper that they made was that some of this seasonal noise was actually becoming part of subseasonal signal that was usable for California precipitation. So we wanted to scale out here and not just look at this particular event or the one after it, and look at this more generally. You know, how well can models predict California precipitation? And so we started designing these plots, and there's a lot here, and you can spend quite a bit of time looking at them. But they give you a lot of information. If you hear the word seamless sweep, this is a seamless sweep. Basically, and let's just focus right now on the ensemble mean. And this is just one model. This is GEFS, ensemble GFS. SubX, of course, has 6 or 7 different models. I can't remember exactly. And the GFS is one of the bigger ensembles. It's 11 members. And the bottom is the mean. And so on the x-axis is lead time. On the y-axis is the correlation coefficient. And then different colors there are showing different window averages. So the dark purple is daily data. And then it goes up to the green line, which is a 35-day average. And there's a dot there because I can't with the 35-day forecast or lead, I can only make one average from that. And so maybe perhaps unsurprisingly, if you take the daily average, it starts dropping below about 0.4 around 10 days into the future, or 10 days lead. However, if you look at a window average like 35 days, it's actually above 0.4. So there's a little bit more skill as that window expands. So yeah, I mean, California precipitation certainly does have skill, but it depends what average window you use, what lead time you're interested in. And a plot like this kind of lets you choose what you want. If you have a certain expectation of skill, you can just kind of use this plot to kind of figure out where you want to focus your attention on. So for example, at CPC, we have this day 8 to 14 day outlook. And so to find the skill at this period, I go to the 7-day window, which is that kind of lighter purple line. And then I draw a line up from the vertical at the lead 8, and that is the skill, about 0.6 for that particular outlook. This is a week 3-4 outlook. So here is a 14-day averaging window, and the skill is about 0.2. And it starts obviously at week 3-4, starts at day 15. So it starts, the skill is mapped there at lead 15. The top panel isn't really the focus of this particular talk, but I like it because it enables me and us to compare between different models. It's a bit of a theoretical estimate. The lower edge of those die-off curves is the single member correlation. So if you take an ensemble member from this particular model, just one, and correlate it against the observation, you get that lower edge. The upper edge is a theoretical estimate from that single member, and it's basically based on perfect model sort of assumptions. So it's a potential upper limit of skill if you were to run the model for an infinite ensemble size. And what I like about that is if I go and I look at another model which has very different ensemble size, I can kind of compare between them. And here I'm flipping back and forth between the FIM model coming out of Esrel and the GFS. And you may notice this, the FIM model tends to jump up a little bit, and especially in that top panel. So there's a little bit of evidence that FIM model has better skill, at least for California precipitation. The other interesting thing about the FIM model is if you look at 15-day lead, that bottom panel, the window averages for those longer periods have more skill than what we see for the GFS. So one of our questions here is, where does the skill come from? Before we tackle that, I want to why I'm using the FIM a little bit more. So, you know, certainly there's a huge collection of sub-X models. GFS and FIM seem to kind of be up there in terms of being among the better models. And FIM has a little bit even more of an edge. And here I do a direct comparison between FIM. And keep in mind, FIM only has 4 members, and GFS has 11 members. So I can create 330 different 4-member GFS ensemble means as a result, using that collection of 11 members, and compare it against FIM. So it's more of an apples and apples comparison. And so anything above that red diagonal line actually means the 4-member FIM ensemble mean has slightly more skill than the 4-member GFS skill. And this is for the 14-day average, just for one average. And I forgot to mention the color bar is the lead time. So these are all the different leads being presented. And so here it is for all the different windows. And as the window period gets longer, essentially what you notice is that the FIM seems to have a little bit better skill than the GFS. So I'm going to focus here on forward, but before doing that, I want to get back to this question about sources of skill. And remember, we've covered, you know, there's this kind of general expectation that there's skill associated with ENSO. But, you know, more recently, why don't we take a look at the wind? And so here I'm just looking totally at observations. There's no model in this particular slide. The left panel is correlation between Nino 3.4 SST index or measure of ENSO and precipitation. And on the right is a correlation between the wind and precipitation. And right away, you can notice over California that the, and I should mention this is for monthly data. So this is not seasonal averages or multi-month averages. These are pooled months over the period that I'm looking at, which is going to be 1999, 2016. And the dots there represent statistical significance. And pretty much what the left says is that, at least in the observations, there is very little correlation between Nino 3.4 and precipitation over California. It's not statistically significant. And this is true even if you look at an extended period. We expanded this out to 82, 2018, and not much there as well. So at least for monthly averages, there's not a lot of relationship with ENSO. Except that it's a very different story when you look at this wind index. Wind index has strong correlations across most of California. And this is one of the reasons that we're looking at California statewide averages. Some people have asked us to split the California into north and south, but what we found is that largely the state of California co-varies, at least associated with this wind index, and it doesn't vary much at all with respect to ENSO. So let's look at the predictability within a model associated with the ENSO and the wind, right? So in these particular slides, I'm not looking at observations at all. There is no observations in here. I'm just looking at Nino 3.4 and California precipitation for the statewide average just within the FIM model. And in this particular example, I'm looking at basically a monthly average, a 32-day average. And so the top panel there is for, it's basically, this is the distribution of California precip, wetter to drier. And it's a conditional distribution. It's conditional based on the model's representation of Nino 3.4. So the top panel is our La Nina cases, or cooler Pacific, and the bottom there is our warmer cases, more El Nino-like cases. And what I hope you see here is that the distribution, conditional on ENSO from that top panel all the way to the bottom panel doesn't change that much. All right, I mean, there's a little bit of movement here or there, but largely the distribution remains the same. So at least within the model, California precipitation isn't shifting around a lot due to Nino 3.4 SSTs. The story is different when you start looking at wind. And the top panel here is when the wind index is weaker, so less onshore flow from the Pacific. And then the bottom is showing where wind is stronger. And basically there's a nice shift here from in California precipitation anomalies from more drier conditions to wetter conditions based on the model's representation of the wind. And you can do this for all of the averages. You remember those averaging windows I was using. I can go from daily all the way up to that monthly. And you pretty much see the same story here, where, when the wind index is weak, you get drier conditions. The wind index is strong, then you get wetter conditions. And this holds no matter the averaging period. You do see some fluctuations here, which essentially is a reflection of central limit theorem. With monthly averages, you have more samples, so it becomes a little bit more Gaussian. But largely, the relationship holds. So some of you might be astutely wondering, well, okay, the ENSO and Precip might not be particularly strongly related, but how about ENSO wind? I mean, there's a relationship between ENSO and jet stream, right? So maybe there's, some influence through the wind. So what we did was we basically linearly removed the Nino 3.4 SSTs in this model from precipitation. We linearly removed it from wind, and then we looked at the precipitation wind correlations or the relationship and how that changed. So this top panel is just showing the full-on precip wind correlations within the FIM model for the winter months. You know, this basically sits there around 0.6, so pretty significant. And it's for the different model average windows from daily to monthly. And obviously for monthly, you tend to have greater correlations in part because you're filtering out more of that synoptic noise. So here's what it looks like when you remove ENSO from both precip and winds. And basically what you see is very little change. The correlations hardly move at all. So basically ENSO is not much of a player, or at least not significant enough player to kind of change this relationship between California precipitation and the wind, at least on S2S timescales. So this is the plot I showed before. It's up here now, just showing winter months from the FEM. And so again, we do have this subseasonal skill. Depends again on the window average and also the lead time. And where is that skill coming from? Well, we would argue it's the wind. So this is a skill for wind. Previous skill for California precipitation. And now I'm going to wind, and it's actually a little bit more skillful. So we would see a lot of the source of California precipitation skills coming from that wind, from the prediction of the wind. Forecast error, all right? So not just how well is the ensemble mean corresponding observations, but rather the difference between them, all right? The forecast minus the observations. On the left here is scatter plot, and this is showing FIM again for a monthly average. And it's precip error on the y-axis and Nino 3.4 error on the x-axis. And it's pretty much scattershot. There's no correlation here. There's no relationship between precip error and ENSO error. But very different story on the right. Precip and wind error is correlated at 0.6. So it's certainly quite an association there, not just for skill, but also for these errors. And so you can do this again for window averages and all lead times. And basically the precip error and the wind error is shown on the top panel, correlation between those. That previous slide was basically showing that green dot, about 0.6. Bottom panel is showing the error correlations for precip and Nino 3.4, and that's basically at 0. So there's really no relationship there at any lead time for any window average. So in summary, despite this apparent failure, although it's not really a failure because ultimately the mean shift is what people often focus on when there is this spread and considerable noise. Do California Precip's forecasts of skill? And, yes, I mean, California Precip has lower skill, especially for seasonal averages, maybe intrinsically because of smaller signal noise ratios. But what's neat is on these S2S timescales, what was once this kind of unpredictable noise actually becomes more predictable signal, and it can describe more of the California Precip variability. So the second question, what are the sources of S2S forecast skill? What are the sources of error? Well, we would argue that a lot of it is not Nino 3.4, at least on S2S timescales. It's mainly the winds that are driving it. And we linearly removed ENSO from the wind, and it still had a strong wind precipitation relationship. These errors were also very highly correlated. So if there's anything to take away from this, maybe to advance S2S forecasts of California precipitation, it might be useful to focus a little bit more on process and tools that would actually result in improved wind forecasts or jet stream forecasts. You don't have to use our particular wind index, but it's a simple way or simple diagnostics to assess it. And I think hopefully these slides have convinced you that an improved ENSO forecast, at least for S2S timescales, probably isn't going to help much. All right, thanks so much here. I think I've finished up. I wanted this last slide. I find the virtual environment to be a little awkward to have a discussion. So, if you don't get a question or you weren't able to articulate the point that you wanted, feel free to just email me after this talk and I will get back to you. Okay, I guess we'll go ahead and open this up for questions and some discussion.
Thank you, Michelle. So if you have a question, just use the raise your hand feature. So be sure to open up the participant box and the button should be right next to your name. To start off, I do see a comment from Matt Newman. I'm not sure if it's a comment, more of a question. So he says, GEFS is not coupled to ocean, correct? Whereas FIM is?
Yeah, that's a really good question. We did take a look at this very briefly. I talked to the FIM folks. So basically, FIM is coupled to the ocean and GFS is atmosphere only. So there is a difference there. Other differences is that FIM and GFS, they share the same physics, apparently, except for deep convective parameterization. Another interesting aspect is that FIM has lower horizontal resolution than GFS. It has the same number of layers, but lower horizontal resolution. So, you know, FIM is probably not doing better because of better horizontal resolution. And also, FIM is initialized with CFSR, which kind of surprised me. This is a reanalysis that can have a few issues. And GFS, of course, is initialized with GDAS.
Great. Question from Joel Wang. Wang, go ahead.
Hi, Michelle. Interesting talk. For the second part of your talk, I have a question about the wind index. How predictable is the wind index, and where does the scale come from?
Yeah, it's pretty predictable. Sorry, I probably did go through this a little too fast, but this is the zonal wind scale. So here I'm just predicting zonal wind, that wind index. So you see for these shorter leads, you know, it can be, it's greater than 0.6. And then of course there's this die-off, you know, particularly in the shorter averaging windows. For longer averaging windows, it does kind of start overcoming some of the skill limitations. So there's a little bit more skill being picked up there.
Where do you think the skill come from? Like, what is the source of predictability for the wind index?
Oh, that's a totally different question. Well, I'm pretty convinced it's not coming from ENSO, at least on S2S timescales. It's pretty much, we've kind of ruled that out, at least in a linear sense. So yeah, I mean, I don't know what sources of skill for wind. I mean, you could say maybe you know, anything from gradients in the ocean, maybe in the Western Pacific in particular. I know there's been work done talking about how gradients in Kuroshio can impact the flow patterns in the North Pacific. You know, there's a whole assortment of different things to look at, and of course, quite obviously, it doesn't have to be a boundary condition. It can also just be coming from a really good initialization of the circulation. So if your analysis is a good analysis, then you're going to get a little bit of skill gain from that.
I also have two questions for the first part of your talk. You showed like a 2-category forecast and also 3-category forecast for, I think, precipitation or temperature, I forgot. My question is, how does the CPC get feedback from users for the different forecast products?
Really good question. So we have CPC, there's some stakeholder engagement, and if you're interested in that, I can like kind of pass your name out. Right now, it seems like the Weather Service focus is more on users that are recipients of our products, you know, such as Bureau of Reclamation and emergency managers and so on. But obviously, academia is a very important user as well as you're trying to improve our forecasts. So, you know, I mean, talk to me about it, but there's different ways we can try and elevate your voice. I know this is a fairly unsatisfying thing, but, oh, okay, something just switched there. But if you go here, if you go to our week 3-4 page on CPC's website, there's an online survey right now. It hasn't closed, so you can click that link and provide some feedback, at least on that particular outlook. Yeah, that's about all I have.
Thank you. Thank you.
Oh, and we also have, I'm not sure how I forgot this part, but we also have our annual climate diagnostics and prediction workshop. And I know a lot of you on this call have been to that, which is great. And it's a good way to kind of talk to the people who manage these products. And it's probably the best way to get a little bit more influence into the CPC process is coming to our meetings and getting to know us better. Oh, and we're going virtual this year. CDPW will be a virtual meeting, so mark that onto your calendars.
Got it. Thank you.
Okay, question from Matt Newman.
Yeah, hey.
Hi, Matt.
Am I connected? I just wanted to.
Yeah, you're connected. I can hear you.
All right. Just to finish up on that comment real quick, the GFS is not just that it's not coupled to the ocean, it's that they use initialized SST that they damp to climatology.
Yes.
So I'm fairly unconvinced you want to use it for any forecasts where ENSO should matter.
Right.
That it's kind of a straw man argument to compare it to. I had a question on the last half first. You're following CPC policy by using NINO 3.4 as a definition of ENSO. Did you try doing that sort of analysis without restricting yourself so much to just the index and look instead at either the SST pattern or actually the changes in the tropical atmosphere that were driven by it? Because 2015 is a nice case where the tropical atmosphere itself is not particularly what you would call ENSO-like, and so it's not really a surprise, I think, that the extratropical response to ENSO doesn't also look so ENSO-like.
Yeah, so I mean, the goal here was to look at predictability within these models. And I certainly, while I showed the GFS forecasts, most of my discussion regarded the FIM. And so I wasn't trying to pose a straw man argument at all. Ultimately, basically, I wanted to answer that first order question about whether SSTs could have any sort of impact on these S2S timescales. And BIM does have a coupled ocean atmosphere, and I would say that the short answer, the quick answer is no, at least with regards to NINO 3.4. The second,
right, but I think that's the thing. You're using NINO 3.4, and you're not looking at the tropics as a whole, and I think that's
let me get to that second part. I was going to get to that part. So yeah, NINO 3.4 is totally fair to, ask that question, and we haven't looked at that in any meaningful way, and it's a good idea. We should do it. I picked NINO 3.4 only because it's so well coupled or correlated with all the other measures that we use for ENSO. So that's one of the reasons I honed on it, at least at this first check. But certainly we could look at UF2, we could look at pattern correlations, and maybe we should do that just to kind of exhaust the options. My gut feeling is that it probably will not, and we should do it, so we should definitely do it, but my gut feeling is it won't bear a ton of fruit, mainly because of what Arun, at least regards to the 15-16 event, which is that the SST patterns are not much different between these best and worst members. So my gut sense, and this is obviously just for seasonal averages, so I've not done this for sub-seasonal, but my gut sense is that the result will be fairly close to this. But I could be wrong. We should do it and just make sure.
I mean, so I think that you're underestimating the impact of the model error, and I think that's one of these issues with these perfect model predictability studies is that the model error may be such that it has a particularly direct impact on something you're forecasting. I think when you're looking at a response to ENSO in particular, the fact that the model likes to shift ENSO to the west and therefore generates wrong sign precipitation anomalies in the western tropical Pacific, that makes it tougher, I think, to use some of these kind of experiments.
Okay, I mean that's actually a really good idea. So what I would sort of say we should discuss and think about is what error term we should measure in order to diagnose this. So for example, this sort of plot where I put Nino 3.4 error, you know, and the Precip error, you know, what sort of calculation should, instead of using Nino 3.4 error, which sort of calculation I should use? And we can discuss that offline. It's a good idea.
So I see a couple more questions. Let's take one from Qinghua.
Hi, Michelle. This is Chinghua. Very nice talk.
Thank you.
Yeah, I have some questions. So I just like to share with you something I learned from my colleague here. So my colleague here, they also do something about this the California precipitation, the seasonal forecast. What I learned from them is something like they like to treat the precipitation separately. But you mentioned briefly in your early part. So they like my colleague here, they like to treat the California precipitation northern part and southern part. So I don't know. Yeah, you mentioned something, but can you re-emphasize that part? Why you think the model you should use as a whole?
Yeah, no, I totally agree with you. I mean, I actually, that's sort of how we started approaching this, but then we kind of realized that there wasn't, we weren't getting any unique information by splitting it into northern and southern parts. And part of that was just because, at least in this particular example, and obviously a different predictor, and these are two predictors, Nino 3.4 and wind, may have a different distribution in California. So, you know, but we were looking at these two predictors, and at least when we do that, we don't see a huge argument for a north-south split. Yeah, and I you know, I kind of wish, I mean, I know we have those really old papers going back in time that have talked about this gradient in California, but the more I look at the data, you know, the longer I'm at CPC, I kind of wish we'd go back and take or reevaluate that. I am kind of curious how that relationship has changed over time, whether we really do have that north-south split. That was kind of, I think, still kind of an open question.
Okay, but how model capture is the gradient, if there is such gradient, or do you see it?
Model, so at least, unfortunately, I don't have the S2S maps for the model, but if you look at a lot of these papers, so this is the Runes and Mingyu's, that top left panel there, that's a signal from CFS, and that's for, you know, that's basically these strong El Ninos, and what you can see, it's all of California. There is a dipole, but it occurs north of California. So that's sort of, I think, the open question is where is that gradient? I'm not exactly sure we know where that is, because I do hear a lot about this north-south California split, and I just have a lot of trouble trying to find it in the data.
Okay, thank you.
No problem.
Okay. Question from Andy Wood. Go ahead.
Yeah, this is just it's a quick question. I've seen a lot of these best four member, you know, worst four member type analyses, and I know the CFS ensemble predictions are a pooled flagged ensemble. Do you know if there's ever been any indication that the kind of weak or best versus worst tend to appear like later or earlier in the pooling? Do you tend to get the best ensemble members out of the most recent initializations?
That's a really good question. Oddly enough, I don't know if you get, do you get Arun's attribution PowerPoint that he sends out once a month?
I do, and I have to confess, I don't read it every month.
I know, it's a lot to get through. So I don't blame you. I don't look at it every month either. But they literally just in the last month, so I recommend just looking at the most recent one, started doing this where they pick out initial conditions closest to the month that they're trying to predict. So the, last, day of the month or last couple days, or I can't remember what they used exactly. And then they also look at members going farther back. It's kind of interesting to look at because you can see the skill, and as one might expect, I guess over a long period of looking at these attribution PowerPoints, the initializing at the end of the month is probably the best for the, when you're trying to predict the month to come. Getting a initial condition as close to that month as possible definitely offers some gains, but not always. On a forecast to forecast basis, it's not a guarantee that it will always be better.
Okay, thanks. I'll take a look.
I mean, it'd be kind of interesting, actually, kind of jumping on that, looking at cases where it did not offer a lot of gain. Like it's sort of the expectation the end of the month would be in most or closest initialized to the target. Would do better, but I'm kind of curious about those cases where you see the reverse and that the members preceding it did better than the ones closest to it.
Yeah, I was thinking that, if it is semi-random, that you get sometimes better initializations earlier, that raises the possibility that you could potentially do some weighting based on how earlier initializations are tracking with various atmospheric features.
Yeah, I think that's a really interesting idea too. There's been a little bit of published literature on that. I think Tim Del Sol did some work on what's called lagged ensembles and looking at how skill varies with lag. Like if you use more members that were initialized earlier than the more recent ones. So Google that paper, Tim Del Sol, and there's a couple others. If you send me an email, I can do the lit search for you, but there's been a little bit of work on that.
Okay, yeah, I see something. So thanks. Yeah, Tim's written a lot of good papers.
All right, let's take one more question from John Nielsen Gammon. Go ahead.
Okay, thank you. Yeah, so I grew up in California, and of course, if we want to forecast whether it's going to rain, we look at the heights and whether the geopotential height is low enough, because that indicates whether the jet stream's in the right position to allow for rain. And when we think about how ENSO affects precip in California or Texas, we think about it affecting the position of the jet stream. So to me, saying that the skill in the subseasonal forecast comes from predicting this location of the jet stream, which is basically what the wind index is a proxy for, doesn't actually explain anything. That's telling us the jet stream matters, but seems like we already knew that. You have to go back. It seems like you have to go farther up the chain of cause and effect to actually get to something useful.
Yeah, so I mean, part of it is nomenclature, right? I mean, so the jet stream is very active synoptically. So it can vary a lot when you look at it on a day-to-day basis. What I think is interesting about this study is that when you start averaging that out beyond a day, as you can see here, the skill actually increases. So what this is saying is that there's a little bit, and by signal, what I'm talking about is the predictable part of the forecast. I'm not as interested in the part that is not predictable or the noise. I'm going to see how much, in that forecast I can actually latch onto and use. And so for that, doing this sort of assessment of where the predictability comes from, even though it's not a boundary condition, is still ultimately useful to know that we're getting some predictable signal on an S2S timescale from this particular type of diagnostic.
I guess what I'm saying is that's the only place that I would expect there to be predictable skill. And also,
Okay. I mean, that's fair. I mean, certainly
you-
there's been a lot of discussion in recent years about how NINA 3.4 and ENSO plays a big role too. And certainly we don't feel that was a major factor in this particular study.
Well, that was my point earlier, that NINA 3.4 affects precipitation through its impact on the jet stream primarily. I suspect there's a lot less variation in the from day to day in the wind index than in the precip. And if you actually correlated instantaneous wind index with the centered 7-day precip, you get something similar to what you get with the 7-day precip versus 7-day wind index.
So, I mean, that's why we did this linear removal, is ultimately we wanted to rule out the ENSO's role in the wind and see whether that made a difference. And this particular analysis, when we linearly removed it, says no, it's really not playing a role in the wind. That's not why we're getting predictable signal, at least on S2S timescales for California Precip, at least not NINA 3.4.
We'll have to talk offline because that's not contradicting anything I've said.
Okay.
But thanks.
All right, so I think with that, we'll wrap up this today's webinar. So thank you, Michelle, for presenting and for the great discussion that happened. Our next webinar will be on July 15th, and we'll continue this theme with Victor Gensini. I believe his talk from the talk title I gathered back in May was Subseasonal Extreme Weather Forecasting, Finding Forecasts for Opportunity. So correct me if that's been updated, but that's what I currently have. So I will talk to everyone in July then. So thank you everyone for joining.